Okay, ladies and gentlemen, Mr. Eisner here, and we're looking at these three problems that seem to cause a little bit of trouble here out of this assignment number 5. So let's go ahead and take a look at these. We're going to start with number 1, I guess makes sense. And the hint that I put out on Canvas or through Remind was that these are all geometric. So if we look at what's going on, we start with x, the next term is x cubed, and the next to the fifth. There's an alternating sign, but we keep multiplying by x squared. So the common ratio here looks like negative x squared. Because we keep multiplying by that, it's causing the negative sign, causing things to flip back and forth. Now, the other thing we know about geometric series is that as long as the common ratio is less than 1, we're going to have this thing converge. So that's going to be negative x squared has to be less than 1. That negative really isn't going to make a difference in there. So x squared less than 1. And under what conditions is x squared less than 1? Well, we could go through a whole process. We could set up a number line, do subtractions, look for factoring. But it should make sense to you here that as long as x is between negative 1 and 1, that's the situation that's going to cause this thing to be convergent. So there's the values of x, and as long as x is here, we're good to go. Now we're looking for the sum. Well, we know the sum of a geometric series is the first term over 1 minus the common ratio, and the first term is x. So this is x divided by 1 minus negative x squared. So x divided by 1 plus x squared. That's what the sum is going to be. Now notice we don't have specific values here because this is a series based on an x, and x could be, well, not anything. As long as x stays in this range, we'll have a convergent series. And then we will get this sum, which is based on x. So that's number 1. Let's go ahead and look at the second problem. If we try to treat this thing the same way, here's what we're looking at. What do we keep multiplying by to move ourselves along? Well, if it's not totally clear, we can certainly do a ratio and set up this common ratio is equal to one term, say 2 over x cubed, divided by the term that comes in front of it, 1 over x squared. Take this denominator and flip it, x squared over 1, and that gets us, we cancel the x squareds with 2 of these, we get a 2 over x, which you might have been able to catch anyway. So the common ratio here, 2 divided by x. Again, in order to determine when this is going to converge, we need the absolute value of 2 divided by x to be less than 1. If we take reciprocals of both sides here, we would say that x over 2 has to be not less than anymore, but now greater than, because we're taking reciprocals, greater than 1. Multiply both sides by 2. Absolute value of x greater than 2. Well, when does the absolute value of x be greater than 2? It's when x is greater than 2, or when x is less than negative 2. And that's the side that you could get if x is negative. Again, we now have our range of values that will cause this to converge. When I go back and find the sum, it's the first term, which is 1 over x squared, divided by 1 minus the ratio, and the ratio is 2 over x. This is complex fraction, so we're going to multiply both sides by x squared over x squared. It's going to have to distribute to the denominator. But that gets me 1 over, distributing x squared minus, and distributing here 2x. And there's the second one. Finally, we go to the third one, and maybe starting to see what's happening here. If we take the common ratio here, e to the negative 2x divided by e to the negative x, that'll be our ratio. Subtract exponents, negative 2x, subtracting the x plus, so we get e to the negative x. That's what we're multiplying by each time. When does e to the negative x take on a value that's less than 1, that's when this will converge. This is always positive. Exponential is always positive, so we just get e to the x less than 1. We could rewrite this as 1 over e to the x less than 1. Again, taking reciprocals, e to the x has to be greater than 1. When is e to the x greater than 1? Again, we remember our exponential curve. Here's 1. Now we're looking at x's that are positive, produce e to the x's greater than 1. So x greater than 0. And that's going to produce this time, as long as that's true, we're going to get a convergent series here. Finally, the summation of this first term divided by 1 minus the common ratio, which is, again, e to the minus x. Not happy about all these negative x's here. So let's multiply by e to the x over e to the x. When you multiply an e to the negative x and an e to the x, you get e to the 0, which is 1. Down in the denominator, we do have to distribute. I get e to the x minus, well, there's that 1 again, 1. And so this would be the sum of the infinite series. In each one of these three problems, we don't have specific numerical answers. They're variable answers because in each case we have variables showing up as part of the problem itself. That's it for those three. I'll see how you guys end up doing on the quizzes, 18 problems, but so far things are looking pretty good there, and decide whether or not I should post anything for those. Until next time, stay healthy.